Hello everyone, and welcome back from the extended spring break. What I've done is created some guided lecture notes and then left space for examples, and I'll make commentary as we go through this. So this is the best I could do. Any suggestions would be appreciated. Last class, we had one class after our last exam, and we actually talked about the method of undetermined coefficients. I'm going to repeat the lecture here for the most part, just for clarity. So, if you recall, if we talk about the general non-homogeneous nth order linear differential equation with constant coefficients, this is the form. So all these little a's are just constants, and we have our derivatives, the nth derivative. But this is what makes it non-homogeneous, is that it's equal to some function. So we had studied on our second exam when this is equal to 0, and that's the homogeneous. And we had seen in the past that a general solution is composed of two parts. What we call the complementary function, which is the solution to the associated homogeneous. So you can see it's 0 on the right hand side. That's what makes it a homogeneous equation. And the particular solution, which is a solution to the non-homogeneous differential equation. So since we've mastered studying solutions to the homogeneous, then our goal now is to find the solutions y sub p to the non-homogeneous. So as we had talked about, you have to make an intelligent guess based on the functions, based on the function involved on the right hand side, what's making it non-homogeneous. And the idea initially is that like are like. That is, since you have a combination of derivatives on the left hand side here that have to give us some function. So you've got the function itself, a function that's the solution y, and a combination of its derivatives that are going to produce some function, then we say that like are like. That is, derivatives of polynomials are polynomials, derivatives of sines and cosines are cosines and sines, and exponentials are exponentials with regards to differentiation. So here's the three examples that we saw last time, and again I'm going to repeat them. And it tells us to use the method of undetermined coefficients to find y sub p for each of the following. So we initially look at this function on the right hand side, and we have to make a guess based on the function. And we have to include all possible combinations in our choice for y sub p that could produce this function. So since it's a polynomial and it's only first degree, we can consider that the particular solution might be of the form ax plus b. So again, you have to include all combinations. If this were only, let's say, x squared alone on the right hand side, then our guess would be ax squared plus bx plus c. So all the combinations of things. And then all we do to determine what these constants a and b are, these coefficients that are undetermined, hence the name undetermined coefficients, is you just take a couple derivatives, because it's a second order linear differential equation. So the first is a, second derivative is 0, and we substitute. And so we'd have y double prime is 0, minus y prime is a, minus 2 times y, which was the ax plus b, and that has to equal the 3x plus 4. So if you want to distribute that -2, by all means do so. And at that point, to solve for these constants, oops, that's a -2b, sorry. We're going to have to compare. So we'll compare, let's say, the x's. On the left side, we have a negative 2ax. On the right side, just 3x. We divide out the x's. Negative 2a would be 3. So a is negative 3 halves. And then the only other thing we can compare is the constants, or the real numbers. And we have on the left minus a, minus 2b, and on the right just 4. We know what a is, so minus 3 halves, minus 2b is 4. So a little arithmetic algebra here. Let's see, and that would give us minus 2b is 4 minus 3 halves, so that's 8 halves, minus 3 halves is 5 halves, so b is negative 5 quarters. So then our solution for y sub p is just ax plus b. A was negative 3 halves, x, and then plus b, negative 5 quarters. Okay, so that one worked out nicely. And doing the second example, here in terms of our guess, I'll make the guess right underneath here for y sub p. It involves x e to the x, and so to include all possible combinations that could produce an x e to the x, we'd have to include ax plus b times the exponential factor e to the x. And at that point, we again are going to, in order to solve for a and b, we could take some couple derivatives here. It looks like the product rule. So first factor, ax plus b, derivative of the second, e to the x, plus the second factor, e to the x, times the derivative of the first, and that's just a. So I'll write a e to the x for y sub p double prime. Product rule again. So first factor, ax plus b, derivative of the second, derivative of e to the x, plus the second factor, e to the x, again, times the derivative of the first, which is a. So a e to the x. I'm going to make this plus a little bit thicker, because then we have to take the derivative of a e to the x, which is a e to the x. And then maybe rewrite this by combining these two a e to the x's. So we've got two of them. Okay, and then we're going to substitute. And substituting, we get, okay, we're going back to the differential equation here. So 4 times y double prime. Okay, I'll use some brackets. Here's y double prime, ax plus b, times e to the x, plus 2a e to the x, and then plus 4 times y prime, excuse me, and y prime is the ax plus b times e to the x plus a e to the x, and then finally plus y, which was the ax plus b times e to the x, and that has to equal 3x e to the x. Okay, so at this point we're going to compare some things. You might want to actually, if you want to just distribute and expand everything and then pick out the common factors or terms, that is. So let's say I'll have 4a x e to the x plus 4b e to the x, that takes care of that. Then the 4 times this term gives plus 8a e to the x. Okay, moving on, we get 4a x e to the x. And then plus 4b e to the x. And then distributing that 4 to this term, we get plus 4a e to the x. And then distributing the e to the x in here, we get ax e to the x plus b e to the x. So you could do your algebra any way you want. That just might make it simpler. But before we go on, let's see if we can combine some like terms. 4ax e to the x here, another 4 of them, and another ax e to the x. So I guess we've got 9 ax e to the x in total. And let's see if we can combine anything else. 8a e to the x, and this 4a e to the x gives us 12a e to the x, and then these b e to the x's can be combined. We got 4 and 4 is 8, plus 1 is 9 of them. So plus 9b e to the x, and that has to equal 3x e to the x. Okay, so now we can compare the, what we're comparing here is actually the, I suppose you could divide out an e to the x, but if you want to compare the x e to the x terms, so we got 9ax e to the x, and that's it, equaling the 3 of them. Divide out the x e to the x, you get 9a equals 3. So a is 1/3. Okay, and then we'll compare the e to the x terms. And we get 12a e to the x plus 9b e to the x equaling 0 e to the x, because there aren't any just e to the x terms on that side. So dividing out the e to the x's, we get 12a plus 9b is 0. Fortunately, we know a, so 12 times 1/3 plus 9b is 0. So that's 4 plus 9b is 0, and b is -4/9. Okay, so then our solution for y sub p is back up here to our guess, ax plus b, so 1/3 as a quantity, 1/3 x minus 4/9, and then times e to the x. Okay, I'm going to make these lectures, video lectures, kind of short. I want to keep them under 15 minutes or so. So I'm going to just call this part 1. We'll go to the next page, and I'll call that lecture part 2.